All right, so planetary motion. There are a couple of things that we learned so far about forces and Newton's laws and things like that. But one thing Newton was also famous for was not just his laws of motion, but he also began to explain why these objects like the moon stays in orbit around the Earth. And so if we define the distance from the center of the Earth to the center of the moon as being like the radius of this circle, like that, I'll just draw a partial of it, Newton came up with this relationship that the gravitational force between the two bodies is equivalent to a constant, which is named for him, so Newton's gravitational constant, times the mass of one object times the mass of the second object divided by the distance between the two squared. Now, in nature, the inverse square, so do you see 1 over r squared, inverse square? That comes up a lot. The attractive force between two opposite charges, like electrons and protons, is a 1 over r squared relationship. The attractive or repulsion forces between opposite or like poles of a magnet are also a 1 over r squared relationship. So it comes up a lot in nature. Okay, so this F sub g is the gravitational force. Capital G here is the gravitational constant. And that number is 6.67 times 10 to the negative 11. And M represents the masses, so mass. And mass would be measured in kilograms, just like always. And R is not always a radius. It is truly the distance from center of mass to center of mass. But you need to think about it as being the distance between the two objects. And it would be measured in meters. So the unit for our gravitational constant, if the gravitational force is in newtons, would be Newton meter squared per kilogram squared. It's the unit there. Now, the Earth pulls on the moon with a gravitational force that is equal but opposite in direction to the force the moon applies to the Earth. And equal but opposite force pairs is Newton's third law. Remember, Newton's third law is that for every force there is an equal but opposite force between our two bodies. So the Earth pulls on the moon pulls on the Earth. Now, we don't notice this motion so much, this pulling so much. It depends on if we see a tide. The tides are controlled by the motion of the moon around the Earth and how the ocean bulges depends on the position of the moon. All right, so if the Earth was like this thing here, and you're sitting here on the Earth, what force is acting on you? If you were to draw the force diagram on the person. Sure. So the gravitational force on you, or a person, would be acting on him and be equivalent to this G M1 M2 over R squared. Now, for a person with maybe a mass of 55 kilograms, that's about 120 pounds, and the Earth with a mass of 5.97 times 10 to the 24 kilograms, and a radius, the radius of the Earth, being 6,378 kilometers, could you find the gravitational force on the person due to the Earth?
Yes.
Yes. Okay, so let's do that. So using these values, the gravitational force on the person would be G m1 m2 over r squared. So the gravitational force would be 6.67 times 10 to the negative 11, that's the gravitational field constant, times the mass of the Earth, 5.97 times 10 to the 24, times the mass of the person, so that's m1, m2. Now, what's the distance of separation?
The radius of the Earth plus the distance between.
Okay, so if you're standing on the Earth, though, what's the distance of separation?
Radius plus the height.
So in terms of 6,378 kilometers, your height doesn't make that much difference. So could you just round it to just being the radius of the Earth? So what is what is 6,378 kilometers in meters? 6,378,1,2,3 meters. So that would be what? 6.378 times 10 to the 6 meters. All right, and then let's square this distance. So grab your calculator. Let's see what that is. So what's the gravitational force between the person and the Earth when the person is on the surface of the Earth? So 538 newtons. Before today, if I asked you to find the gravitational force on a 55 kilogram person, what would you do? You would use the mg, and you'd do like 55 times 9.8. What does that give you? 539 point. Okay. Are these two numbers really close? Probably difference in some rounding or something. Oh my goodness. So the gravitational force that you've been calculating all year long is the gravitational force between you and the Earth, which is equal to the force that you apply to the Earth. Now, let's look at this a little bit deeper. That means that if the gravitational force is the gravitational force, yeah, that looks silly. That means that m times g would be equal to g. I'm going to use a big M to differentiate a little m over r squared. Well, look, little m can cancel out. Maybe little m is the person sitting on the Earth, and big M is the mass of the Earth or the moon or whatever planet you may be on. So then the gravitational field constant can be calculated as Gm over r squared. Now, at the surface of a planet, the gravitational field constant would be G capital M over the radius of the planet. So a lot of times we use a little r to represent a variable, and we use capital R to represent a particular value, such as the radius of a planet. So if you want to know what the difference is, a little r is usually a variable r somewhere around it. So I could calculate the gravitational field constant at the position of the moon if I knew the distance from the Earth to the moon. I could calculate the gravitational field constant at the top of Mount Everest if I knew the height of Mount Everest and added it to the radius of the Earth. So the gravitational field constant depends on your position. You can find the gravitational field constant on you while in an airplane if you add the radius of the Earth to the height of the airplane. So this will give you the gravitational field constant of any mass at any distance. Even yourself, because every mass is attracted to every other mass. We're just on the Earth, which is a big, big mass, and it attracts us all, and it's overpowering, and we don't notice the force of attraction between small masses. All right, so let's look again at this motion of the moon around the Earth. Okay, so I'm taking the Earth and the moon because those are the two bodies that you are most intimately involved with. Okay, so the moon is attracted to the Earth by this gravitational force, but it's going around the Earth in this approximate circular path. It has a tangent velocity, but the Earth is always pulling it back in. The moon was probably a failed planet or a piece of another planet that got trapped in our orbit. So it was flying by us at just the right speed and got trapped. Or a big giant comet hit the Earth and ejected part of the mass of the Earth and it became the moon. There are all kinds of theories on how we got our moons or how moons are formed. So anyway, this force is pointing towards the center. So that means the gravitational force is centripetal, which means that capital G, mass of the planet, mass of the moon, over the distance from the center of mass of the Earth to the center of mass of the moon would be equal to the mass of the moon, or the small orbiting object, times v squared over r, where r is still the center-to-center distance. All right, so if I reduce this, I get what? G capital M over R is equal to V squared. So V is the square root of GM over R. This is a special speed we call the orbital speed. Still measured in meters per second. This is the mass of the thing being orbited. So this is the mass in the middle. This is the distance from center to center. Center of mass to center of mass. Okay. Now, when we did our swinging the stopper around and around our head lab, we also used another expression for velocity. Do you remember what we used? It was the distance the stopper went divided by the time to go around. Very good. So we could also set this equal to 2 pi r over period. Oh, if I do that, then let's see. I'll have 2 pi r over period is equivalent to the square root of capital G, capital M over R over R. So could I isolate the period and determine what the period depends on? This is what Kepler worked on. So if I do some math here, I can square both sides, and I'll have 4 pi squared r squared over period squared is equal to capital G, capital M over R. So then 4 pi squared r cubed over G capital M is period squared. So the period would be the square root of 4 pi squared r cubed over GM. Now, I know you could reduce that and pull out the 4 and the pi, and you can if you want to, but traditionally we just leave it like this. So what this proves is that the period is proportional to the radius. And it's proportional to the radius as what? 3/2? So as the radius increases, what happens to the period? Does it get bigger or smaller? It increases. And that should make sense a little bit in your brain when you think about something far from the circle moving slower, things, when we see the models of the planets. But then what about the mass of the thing in the middle? So if our sun was bigger, the mass of the sun was bigger, what would happen to the period? Because it's related to 1 over the square root of m. So if our mass gets bigger, the mass in the middle gets bigger. The period actually gets smaller, so we go faster. Zoom, 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 zoom. Okay, now the next thing that we can apply to this planetary motion. Remember, we found gravitational energy as being mgy, and that was for something close to the planet Earth. And now we know that little g is really big G, big M over r squared. So, that was when we were using g as a constant because we had a number based on the mass of the Earth and the radius of the Earth. Well, what if I want to find the potential energy of the moon-Earth system? Well, the moon is not on the surface of the Earth, and it's far away, and it's further away, so the gravitational field constant is going to be much, much smaller. So if you remember, potential energy is equal to the negative integral of the force with respect to position. So that means that I could find gravitational potential energy, and you can call it E sub g if you want to, as being the negative integral of the gravitational force times dr, or by dr. Now, U sub g then would be negative. The gravitational force is always pointed down towards the center of the Earth. So we're egocentric. Let's make it a negative g m over r squared dr. And let's integrate from infinity to r. So we're going to start with the moon very, very, very far away, and we're going to bring the moon or whatever object it is into a position r. So when I integrate that, that would really be what? The integral from infinity to r of capital G m over r squared dr, which should be negative G m over r from infinity to r. So why use infinity? So here's the analogy. Here's the Earth. Let's say you have an object at these different positions. Okay? And as that object falls and moves in this direction, is the gravitational potential energy increasing, decreasing, or remaining constant as it falls towards the Earth? The gravitational potential energy? So EG is mgy. So we've got this y, this y, this y, and this y. At what place do you have the most gravitational potential energy? At the highest point, we have the most. So this is the greatest gravitational energy, and then down here we have the lowest. I'm talking about just something in the classroom height. It doesn't have to be out in space. Okay? So as we go, this is the most to the least. Okay? And I need to have a place where my function can zero out. Because like we have zero potential energy in terms of the Earth ball system when the object is at its surface, right? So I pick infinity because when I do this, if I get to finish it up here, we'll have negative g m over r minus plus, right, minus the negative over infinity. So what is gmm over infinity? Right, it goes to 0. So now I have a reference that is 0. And the negative sign is still left there, so that in general my gravitational energy would be negative g m over r. So the maximum gravitational energy between two bodies is 0. And then any place closer to the Earth or closer to the body than infinity, it's actually lost, or there's a negative gravitational potential energy. So think about it. So using this gravitational potential energy equation, if we look at a satellite or a planet or something orbiting, so let's take the Earth and a satellite, for example. So this satellite is moving around the Earth. It's at a position r from the center of the Earth. So it would have gravitational potential energy. But what else would it have? Because it's moving around the Earth. It does have inertia, but it has kinetic energy because it's moving. So the total energy of the satellite would be the kinetic energy of the satellite plus its gravitational potential energy. Because the two bodies are far away, not within reasonable distance as the radius. So that means that our orbiting mass would have a kinetic energy of 1/2 little m v squared minus capital G, because the gravitational potential energy is negative gmm over r. So capital M, little m over r. Now this v is the orbital velocity, the orbital speed. So could I substitute the square root of gm over r for the velocity? And, let's see, that means that 1/2 of the square root squared, so g capital M little m over r minus capital G capital M little m over r. Oh, what's that? Negative 1/2 g m over r. So this is a way to find the total energy of an object in orbit. The total energy of the object in the orbit. We can also then determine the escape speed, like how fast does an object have to be moving at the surface of the Earth to be able to escape the gravitational field of the Earth, or where it's at least significant. And we'll do that next.